All right, let's go on to the next chapter, which is here. Okay, core defense mechanisms. And make sure everything's working. Looks pretty good. Okay, so here's what you can do to stop people from hacking your website. You can limit their access to part of the site that they shouldn't be getting in. You can restrict what user input they send in, what kind of characters they send up. You can make it difficult for attackers to attack you by slowing down response or frustrating them. And you can monitor the application to notice when people are doing suspicious things and prevent them. So the basic things you do to handle user access are authentication, session management, and access control. And unfortunately, all these things had to be bolted on to HTTP after it was designed. It was originally designed without any of these, and the techniques we use are all added. So authentication, somehow you have to prove who you are. Typically use a username and password, which as we know has its own weaknesses. It's better if you have two-factor authentication or something, or smart cards or client certificates, or common access cards in the military, something like that. And then the other considerations are users might make their own account and choose their own password, and you might have some way for them to recover a lost password or access to an account that they've been locked out of. And those are often weak spots where an attacker can get in. So you have a login function with the username and password, and you often have rules like this. It must be a certain number of characters and include numbers and uppercase and lowercase and things like that. So people usually have predictable usernames, and if they choose their own password, they often choose really obvious, predictable passwords. And there are various other logic difficulties that occur, like letting people... one thing that's happened quite often is that there's a password reset system where you fill in some kind of information like your personal information, and then it sends you a URL to click to reset it, but the number in the URL is not really random. And I can find out that number that would let me reset your password. That happened to Facebook and a lot of other websites. All right, so then there's session management. After you log in with a user and password, if nothing goes wrong with that, now I somehow have to keep track of the fact that you're logged in, and all my future requests to the server have to somehow prove that you have already logged in. So you typically do that with a cookie, a Netscape invention from long ago, where it sends an extra bit of data along with every request. And that cookie will presumably match some number stored on the server that I can use to tell that you have logged in. And you have some kind of session management where that cookie will expire after a certain amount of time, perhaps, although these days it usually doesn't, because people do things like log in on a cell phone, and it's irritating to type in the password again, so they just use the same old cookie for a really long time. So one common mistake is that the cookie is not random enough. It can be guessed, or the tokens are handled poorly, so somebody else can steal your token. For example, as we said earlier, through cross-site scripting, I can trick your browser into sending me your token. So once you get in, and you have a token to prove that you have in fact logged in, then there should be access control. I should be checking to make sure that that token gives you the authorization to do whatever you're doing. That's what I mentioned earlier about insecure direct object access. It is quite common that there's a page doing something of high privilege on a server that forgets to have any access control. It doesn't actually check to make sure that you have the right token. So if you find your way to that page, you can perform a high privilege action without really previously logging in. I see a question. Can you perform XSS on something like JSON web tokens? Yes, I think you can. You can steal anything in the cookie in principle, unless it is marked HTTP only. You can get it with JavaScript. And that's typically how cross-site scripting works. So, all right, so you have user input. People are filling in forms like first name, last name, email, and phone number, and then they will have some limitations. And the point is, this is called input validation, where you take the input from the user and verify it before letting it go to the server. That's fine, but you can't trust it, because if they're using something like Burp, they can bypass that typically. So you have people typing in blog posts, cookies, parameters, and other fields. Yes, you're going to perform a lot of cross-site scripting. Yeah. We'll be doing all these things hands-on in the projects. You'll get used to it. And so the other thing, so the simplest technique that's commonly used is to reject bad characters. So you just try to recognize characters that are dangerous or patterns of characters that you don't like and block them. This is called blacklisting. People call it bad listing now to try to be less offensive. And the point is, the word select might be blocked because it's part of a SQL injection, but if they block it this way, you might be able to just change the case of the characters and it might not be recognized that way. This is the problem with blacklisting. You have a list of known bad things, and that's just the challenge for the attacker to find a way to change it a little bit so it's no longer on your list, but it still has the bad effect. And there are many ways to change things in small ways here. Like another thing you can do is instead of having select space, you can put a comment instead of the space, and now it will not find the word select followed by space. There are many techniques. Here's another thing you can do. You can put a hexadecimal null byte before your injection code, and this exploits something that the web server is typically using HTML encoded data, so a null byte is fine, but the web application firewall is typically running code written in C, and in C, a null byte terminates a string. So the security device will probably not look past this null byte, but the web server will. So you can hide your forbidden content here and the filter won't see it. All right, and this is a fine example of what we're going to be doing with this whole course, which is the part where you have to get kind of used to this. You have these strange constructions, and they're usually mixing two different languages. Yeah, 00 and a get parameter will break the request. Well, that's good to know. I wonder if that depends on the server. In fact, I have it in the parameters in my 127 class. You can totally put it in the parameters, and it works. I'm using it in get parameters. So that depends on your server. Well, if you take in 127, we'll be using that later. You can use arbitrary code, including null bytes, in the get parameters, and it works. Anyway, so what's considered much stronger than blacklisting is whitelisting. Like I say, it should probably be called good listing these days. The point is, instead of trying to illuminate all the bad things that could happen, you just have a limited set of good things, and you only let things in if they are recognized to be on the good list. This is a lot better. But sometimes you can't really do it. Like an apostrophe is a dangerous character for SQL injection, but apostrophes are actually used in real printed text and in names and stuff, so you probably can't just block apostrophes entirely. So the good listing is not really going to save you from that. Deny list and allow list are the preferred terms. Oh, good, thank you. Those are good terms. All right, so sanitization is another practice a lot on the web, which is pretty horrible, where you have an input, and the input contains some bad stuff. So you just remove the bad stuff and keep using the rest, instead of just rejecting the whole thing for having bad stuff. This is very common. So you use HTML encoding, so characters like space will turn into this. Any character can be expressed with a % and 2 characters for hexadecimal. And that's one way to do it, to try to sanitize things, to remove the dangerous aspects of the bad characters. But what's better is boundary validation, which we're going to get to. So safe data handling is writing code that cannot be fooled by malicious characters. SQL, you use parameterized queries, so it cannot misunderstand a data item as a code item. And you don't use command CMD in PHP or the equivalent, where you use system commands, which gives you the bash line command injection. So if you just write better code, it's harder to fool, and that's called safe data handling. You can also try to do semantic checks. For example, if you just try to block all apostrophes in something in case of SQL injection, you could do that, but it would be a lot more effective to understand what service you're trying to protect and carefully block the input that is dangerous for that service, and indeed the content based on the context. If you're at a bank, then you should make sure that every account number in the request is in fact owned by the currently logged in user, for example. That sort of thing would be a semantic check to make sure the data is reasonable in the context in which it's being used, and that would be much more likely to detect a malicious input. And so, simple input validation, will have trouble with this because your apps probably have several steps going to different servers, and data harmless at one stage might be transformed into something harmful at another stage. And the simplest example of that is SQL injection, where you are sending a request to a server that is doing something like search for a user, and you're tricking it into dump a list of all the users, but it's not like there's an error or an error message. You're sending a request which is properly formatted and executed properly. It's not exactly a bug. It is just an unexpected ability to use the services operating as designed to have an unexpected result. All right, so I mentioned before in the news talking about zero trust. This is the concept you need, boundary validation. You have to have zones, and on one side of this, input is trusted because it's been cleaned, and on the other side, it's not trusted, and you have to clean the data that passes the boundary. You have to define the boundaries in your network and check the data as it passes. So each component should treat the input it gets as possibly malicious and perform validation instead of assuming that you can trust it. So you'll have a network like this where user is going to log into a server, and then the server is going to perform a SQL query up here, perhaps to find out the correct password hash or something, and then it's going to send a SOAP message down here to access something like stored files. And so each one of these can have its own request. So you'll have a sanitization here as the login data comes in, and then you have another sanitization here to look for bad SQL commands, and another sanitization here to watch for bad SOAP commands coming in. Each one of these servers can check the input to make sure it's not bad as it comes in, rather than assuming that since this input came from a server at the company, it must be okay. You can't make that assumption. And by the way, this is what SOAP looks like. SOAP is a lot like Simple Object Access Protocol. It's a lot like HTTP. It's another way to fetch data and files from a server. So your app might check only for good characters, limit the length. The SQL query would then escape dangerous characters like apostrophes. The SOAP service would block XML meta characters, we'll talk about later, which are something you can use to inject code into SOAP requests. And back when it sends the user's account information back to the browser, it would be HTML encoded. So if I had cross-site scripting, where I could store some data on a server, and then when another user looked at it, the account details would include scripts. You could do output encoding here, where when sending data to be displayed in the user's browser, you URL encode it so that it will not take less than and greater than characters literally. It will express them as ampersand LT semicolon and ampersand GT semicolon, which will look like a less than or greater than, but will not be misinterpreted as control characters by the user's browser. That's output encoding. Someone says, what does a SOAP request require? Well, it's just another protocol, a lot like HTTP. So it just sends a request to the server. You see it here. It's a post request just like HTTP, but down here it's XML. It's one of the many XML-based protocols. So, and the meta characters here are things like less than and greater than. You can have things like XML entity injection. You can inject extra XML headers, which cause the server to do unexpected things. A little bit like SQL injection. And we'll do that as we go on later in the course. All right, so the filtering is a lot harder than you might think it is. So if you don't want to let people do cross-site scripting, you might want to stop them from putting in script. But the attacker could just send this. And then when you remove script, you have another script left. So one pass of removing script will not be enough to prevent us from injecting a script. If you want to block directory traversal, you take the URL and you put .. / to move up out of the folder where the web page lives into other folders on the server. So if you don't want to allow that, you can remove .. and .. backslash, but if you do it in this order, I could send this string, and it will first look for .. and not find it. It will then look for .. and remove it, and the end result is .. So again, it's harder than you would think to remove bad things, which is why, deny list is a poor security policy. Another one is canonicalization. you URL encode data. So an apostrophe is expressed as %27, 3 characters, which will be interpreted as a single apostrophe by a web server, but not by other servers like a SQL server. So that's fine. But the problem is Microsoft IIS, and I think other products, would decode URLs twice by mistake, so you could double URL encode it. %2527, when decoded the first time, the %25 would turn into %, and decoded another time would turn into an apostrophe. So this strange structure would be interpreted as an apostrophe and have the effect of a SQL injection. So here's some things to handle your attackers: errors, logs, alerts, and reaction to attacks. Yep, good. I see another good comment there. All right, so one common thing that happens on web servers is they have error messages that are far too informative. So here, you go to a website that's got a problem, and it gives you SQL injection, unexpected end of command, and then it gives you more information, tells you version numbers, and so on. If you don't handle errors, the default error from products is usually far too informative. You do not really want to tell the end user what version you're using of things and such. Then there's audit logs. You should be logging events on the server. Certainly, most servers will audit failures, like login errors, because they indicate brute force attacks. I mean, it would be nice to log every client request in full, although that's expensive. That will make a big log and use a lot of your server processing time, but it's the way to really find out what's going on. But anyway, you can compromise by doing the high-value activities like credit card payments and so on. You should be logging suspicious traffic on your server so that when you're under attack, you can go back and have some attempt to reconstruct what happened. And you should, in fact, be passing those logs to a central log server like Splunk, where you can analyze them. So your logs often contain confidential information. They usually contain cookies, they might contain usernames, maybe even passwords, so you should be aware that logs shouldn't be just stored in a publicly accessible place, and attackers will often try to erase the logs, of course, so they should be on something that the attacker cannot erase, like a write-once media. And when something bad is happening, you should be alerting the administrator. So set up something like too many requests from the same user or large funds transfers, things like that. Things that look really suspicious should send an alert to a human who will then investigate. I remember one of my students worked at Cloudflare. I shared a room at DEF CON years ago, and they were being woken up at like 2 a.m. because they were on alert. Cloudflare has automatic defenses, but if it can't figure out what the automatic defenses, each one of the people on the team has to take turn being on for like a few days, receiving the calls. So you had to get up and analyze this traffic. So firewalls, web app firewalls, are boxes that are designed to achieve compliance with standards like PCI DSS, so they will always pass the audit tests. And so they detect certain attacks, but they'll only do generic attacks. They are not customized to your company. So they'll just have a list of generic attacks, and there are often ways to exploit your servers without violating the rules of the web app firewall. Avoid security roles that require you to be on call. Well, yeah, it's an issue. Yep. Anyway, so the most effective security control would be customized to your application, but of course that requires some custom work on your side and some security expertise at your company. So hackers probe for vulnerabilities. They run vulnerability scanners, they run brute force attacks, and so on. So you can defend yourself by detecting suspicious traffic and just kick off anybody who's suspicious. This is what Bro did, the product now known as Zeek. That was its main defense. If somebody did something bad a few times, they would just block that IP address for half an hour. And they said that was really extremely effective. Another thing you can do is tar pit them, where you respond slowly to their requests, just to slow down their tool and frustrate them. So there's a management interface. Typically in your content management system and your other devices like firewalls, you have a web page that you can log in to control it, and that is something people can attack. They can DDoS it, they can do a brute force attack to guess the password. That's a fairly high value target, your management interfaces. Another thing to be aware of. And people can attack the administration panel like we talked about. And if you have cross-site scripting, then somebody could implant a cross-site scripting payload somewhere where the administrator will see it, and then they might be able to steal the administrator's cookie and then log in as the administrator. And that sort of thing has happened many times. So let's take a look at another Kahoot, and that'll be enough for today. Here's the Kahoots. 129S, Chapter 2. I found 2 students that wanted to add, and I just approved you, so you should be in. All right, looks like we got everybody. All right, so what does logging in do? Yep, that's authentication, proving who you are. All right, so how does a website remember who you are? That's session management. It has to, typically with a cookie, it has to record who you are and that you are currently having a logged in session. All right, what process requires writing code that can't be fooled? All right, that's safe data handling. All right, what happens when you remove the malicious part of the input and use the rest? That's sanitization. All right. All right. All right, and Goodwood Alchemy is won twice. And Eileen. Eileen is won twice. Good. All right. So I've got my winners.